Okay, so we are talking about the chi-square test for independence or association instead of goodness of fit or homogeneity. This is the same test. You can call it either one, chi-square test for independence or chi-square test for association, and I usually just decide based on what the wording of the question is. So two-way tables can arise in different ways. The chi-square test for homogeneity is used when we compare the distributions of categorical variable for multiple subpopulations or treatments. But when we are talking about, how do I move that? There we go. When we are talking about the chi-square test for independence or association, this is when a random sample from a single population is classified based on two categorical variables. So instead of looking at different, I won't say populations for the homogeneity, but different subgroups of a population versus one categorical variable or different treatments, the chi-square test for independence or association, we take one single sample instead of a stratified random sample from a population, and then we classify based on two different variables and make it into a table. So a chi-square test for independence association is used to determine whether the row and column variables in a two-way table of categorical data might be associated in the population from which the data were sampled. Okay, so let's go through our steps in a chi-square test for independence or association. Our first step is to state our hypotheses, right? These are pretty easy in a chi-square test for independence or association. We can either for the null say blank and blank are independent in the population of blank, and then the alternative, you don't have to put all the context in, you can just say they are not independent. Or if you decided to name it a chi-square test for association, then you would say there is no association. The same thing as saying they are independent. Independent variables would not be associated, right? They would be independent of each other. If there was an association, then they would depend on each other. So there's no association between blank and blank in the population of blank. And then the alternative, there is an association. So maybe I'd say for the null that gender and IQ score are independent in the population of all Free State students. And then the alternative, they are not independent. Or I could say there's no association between gender and, what did I say, IQ score in the population of Free State students versus there is an association as the alternative. So then for step 2, what do? Yep, name our procedure, and that's really easy. We call it either our chi-square test for independence or we call it our chi-square test for association. And then our good old step 3, right, we are going to check our conditions, and this time they're a little different, right? We don't sin, we SIE. So the S is the same as it's always been. The data need to be from a random sample from the population of interest, and again, I want to point out we're talking about a single random sample versus a stratified random sample for a chi-square test of homogeneity. That really helps me decide which kind of test it is if the wording of the question isn't clear. And obviously, it's going to be from the population of interest, and they'll have to tell you that in the question. And our I is the same as it's always been. When sampling without replacement, we have to check that our lowercase n is less than 10% of capital N and show that check. And then all expected counts must be greater than 5. and you have to show your expected counts. Again, just like in the chi-square test for homogeneity, not like the goodness of fit test. The expected count is just your row total times your column total divided by the table total, or what I usually say is the grand total. But remember, our calculator will give us this in the matrix when we run the test. So I don't actually use that formula very often when I'm calculating expected counts, maybe in the multiple choice section of the AP test, but never in the free response section. Okay. So then what is step 4? Yeah, step 4, my favorite step, do the math. So what math we need to do, right? We need to calculate our chi-square value, which is the sum of the observed minus expected quantity squared over expected. I could have written that a little bigger, huh? Maybe I will do that. Chi-square is the sum of the observed minus expected quantity squared. Oops, that's supposed to be a squared. I don't know how I got a degree symbol. Squared over expected. And you need to find the p-value, which again our calculator should give us. Whoa, scrolled way back. And we need to find our degrees of freedom, which is not like our goodness of fit test. It is like our test of homogeneity. So we take the number of rows minus 1 times the number of columns minus 1 to get our degrees of freedom. And then our conclusion is the same as it's always been. Our conclusion in context would be, because the p-value, whatever, is greater or less than alpha, whatever, I reject or fail to reject the null hypothesis. There is or is not evidence, and then I state the alternative. Okay? All right, so let's try one. How about this? Are men and women equally likely to suffer lingering fear from watching scary movies as children? Do you guys know any scary movies that you watched as kids? Researchers asked a random sample of 117 college students to write narrative accounts of their exposure to scary movies before the age of 13. Of the 38 males surveyed, 7 said that some fright symptoms are still present when they are awake. 29 of the 79 women surveyed said the same. So assuming that they didn't lie and those answers are legitimate, then let's carry out a test to see whether men and women are equally likely to suffer lingering fear from watching scary movies as children. I remember watching The Birds, that Alfred Hitchcock movie. That still, well, I guess if I watched it today, it probably wouldn't be really scary because the effects are really bad, but that was scary to me as a kid for sure. And I rewatched Cujo recently, and that one is still really scary to me, especially even more scary now that I'm a mom. Ugh, never will I own a St. Bernard. Okay, so on our table, what are the 2 variables that they are looking at? So you saw they took one single random sample of college students, and then they classified them based on their gender. They had males and females, and the fright symptoms, or whether or not they had fright symptoms. So how about we put gender here and say male, female, and I always like to put the totals on there. And then we could say, I don't know, lingering fear. How about? And we can say, yes, they have lingering fear, or no, they do not. And again, we can put the totals in. So then we'd have our 38 males that were surveyed. So male total is 38. 7 said that they had lingering fear. They had some fright symptoms still present. And that would mean obviously 31 did not. For the women, 29 said yes, they still have lingering fear out of 79 that were surveyed. And so that would leave 50 that are not. So again, for people that aren't careful with their statistics, they just see that 7 men and 29 women, and they go, oh, well, clearly men aren't scared nearly as much as women, but that's not taking into account that the sample sizes are very, very different. So I can add these up vertically and find our totals here too. This would be 36, this would be 81, and this obviously would be 117 because that was our total. Okay, so then what are the steps we need to walk through? What is our first step? Yep, state our hypotheses. So what would our hypotheses be for this? So this one didn't say either association or independence. I might use the word association, but I could write it as independent as well. I could say the null is that there is no association between gender and lingering fear for the population of all college students. And then the alternative obviously would be there is an association. Yeah, that is how I worded it. But I could write it the other way too and say gender and fright symptoms, or I guess I said lingering fear before, either one, fright symptoms or lingering fear. For the population of all college students, and there is an association, I can say that gender and lingering fear are independent for the population of college students. And then my alternative, they are not independent, or I could say they are dependent. Since I said association in my wording, although it wasn't in the question that way, so you could really write it either way, I'm going to say this is a chi-square test of association. If I had written it in terms of independence, then I would say it's a chi-square test of independence. But make sure that you don't get those mixed up, which one's the null and which one's the alternative. I always think about this as if I see two people walking down the hall together, I don't assume that they're dating unless I have evidence, right? So I assume they are independent or there's no association between the two people walking down the hall unless I see them holding hands or making out or whatever. And then I have evidence for that association or that they are not independent. But that's what I always think of, just two kids walking down the hall. Okay. So then our step 3, obviously we have to check our conditions. And so we're going to see SIE if the conditions check. So our S check, it was stated that this was a random sample of college students. So we're good to go on that one. For the I, we would have to check, because we were sampling without replacement, that our lowercase n is less than 10% of our capital N. So 117, our sample size has to be less than the population, or less than 10% of the population of all college students. And so there have to be more than 1,170 college students. Well, obviously there's more than that at KU. So the observations can be considered independent. And then for our E, right, we need to check our expected counts. We need all of our expected counts to be greater than or equal to 5. So I was just going to make a new chart here and say lingering fear, yes, no. I don't even need the totals. Gender. Did I do male first before female? And again, I don't need the totals because I'm really only worried about those expected values. So remember, we need to put our data into our calculator as a matrix. So let me go back to my actual data so I can see. And remember also that you're not putting in the totals, you're just putting in the counts, okay? So 7, 31, 29, 50. All right, so if I go to my camera, let's see, there we go. Turn my calculator on. Okay, and go to second matrix, and I'm gonna edit matrix A. And since there were 2 rows and 2 columns without the totals, then it's a 2 by 2. And what did I say it was? 7, 29, 31, and 50. I think. Let me go back and double check just to make sure. Oh, nope. I was wrong. See, it's a good thing I checked. I mixed them up. Oops. It's 7, 31, 29, and 50. Okay, let me fix that. So 7, 31, oops, 29, and 50. Okay, so then, even though we're still checking the conditions and we shouldn't do the test until we're sure that the expected counts are all greater than or equal to 5, in order for the calculator to give me the expected counts, I have to actually run the test. So I'm going to do stat over to tests and up to the chi-square test. Remember, not the chi-square GOF, goodness of fit test, just the chi-square test. So I'm going to hit enter on that. My observed are in A. It's actually asking where we want the expected, which I love. Yes, go ahead and put them in B. Calculate. So now it gave me my chi-square statistic, and it gave me my p-value and degrees of freedom. And so I usually go ahead and write those down, but I think I'm going to come back to this in a sec. I'm going to go ahead and look at the matrix, and we want to look at B. B is 11.623, and then 26.308, and then 24.308, and then 54.692. So those are obviously all greater than or equal to 5. So let me go back and write these down in the table. So we had, what was that, 11.692 and 26.308 and 24.308 and 54.692. And all expected counts are greater than or equal to 5, and they can see them right there in the table. Okay. All right, so now we can actually do our math. And so we are going to find our chi-square value. Remember, you have to show your work, but you can use an ellipsis, so we don't have to write out every single step. But we are going to take the sum of our first observed was 7, right? I'm not going to mix them up this time. Okay, 7 minus our expected 11.692 quantity squared over 11.692 plus, oops, I can't do an ellipsis yet. I need to write my second one down. Second one was 31 minus 26.308 quantity squared over 26.308 plus, now I can do an ellipsis, plus, and then I can write my last one down. We had 50 minus 54.692 quantity squared over 54.692. And when I ran that test in my calculator, which now I have to do again, but that's not a big deal, I got a chi-square statistic of 4.028. And my p-value, again, from my calculator, was about 0.045. And my degrees of freedom was, we had 2 rows, male and female, without the totals, right? -1, times 2 columns, lingering fear yes or lingering fear no, not the totals, -1. So 1 times 1 is obviously 1. That was what the calculator said too for degrees of freedom. Okay, so what would our conclusion be? Now, remember, we had from the question, where did it go? We were asked to carry out the test at the alpha equals 1% level, or the 0.01. So don't forget that when we're writing up our conclusion here. So because the p-value, 0.045, is, greater than alpha, which equals 0.01, I failed to reject the null hypothesis. There is not evidence of an association between gender and fright symptoms or lingering fear. In the population of college students. And again, you could say it if you'd written your hypotheses as independence instead, then I would say there is not evidence of gender and lingering fear being dependent or not being independent of in the population of college students. Okay. And so tonight's homework, maybe figure out if you can see what all these movies are. That would be fun. And page 878, number 29 and 41, just do parts A and C. Page 878, 29, and 41, parts A and C.